Last week we talked about the normal force and how we kind of said the normal force is what a scale would read. Like if you were standing on a scale, the normal force of the floor pushing up on you would be like what the scale would read if you're standing on a scale. I also want you to recognize that you might hear the term apparent weight. The normal force is also the apparent weight of an object. So the weight of an object is always the force of gravity acting on it. But the apparent weight might change depending on what else is happening. Um, so, for example, when you're holding on to something, you can describe how heavy that object feels to you. Let's say you're underwater holding a bowling ball. The bowling ball is not going to feel as heavy to you because the buoyant force is pushing up on it. So the apparent weight is different when you're underwater. The weight is still the same. The actual weight is still the same because that's a force of gravity acting on the bowling ball. But when you're underwater, the apparent weight is different. Okay? And apparent weight is also kind of talking about what the normal force is. So you can think about when you're holding something, you are exerting a normal force on that object. There's a force, perpendicular to the surface of your hands, pushing on that object to hold it up. That's a normal force. And that normal force is the apparent weight that you are supplying, that you feel like you're holding it with that much weight. So these can also be thought of as the same type of thing. When is the apparent weight different than the force of gravity, your actual weight? That's like saying, when is the normal force different than your weight? When is the scale read something different than your weight? Well, we talked about one example just now is when you're underwater. Obviously, the scale would read something different if you weighed yourself underwater. Your apparent weight is different when you're underwater. The normal force acting on you is different when you're underwater compared to your weight or the force of gravity on you. But we're going to save talking about underwater until later in the semester. For now, there's three main times when your apparent weight or also your normal force will be different from your actual weight, from the actual force of gravity on you. One case is if there are other forces acting in the vertical direction. Okay, so for example, let's say you're standing on a scale, but then there's a tabletop nearby, and you lean on the tabletop with your hand. Think about what that would do. So you're standing on the scale, but you're leaning on the tabletop with your hand. Your scale is going to read less than your weight because now the table is also pushing up on you, supporting the force of gravity, supporting your weight. So your normal force is going to read less than your weight. The scale is going to read less than your weight. The normal force acting on you will be less than your weight. Your apparent weight in that case is less than your weight. That's because there's another force acting on you in the vertical direction. Another case where those are going to be different is if the object is accelerating in the vertical direction. And that's something we saw last week when we looked at the example of a man riding in an elevator. When a man is riding in an elevator, if you ever try to weigh yourself in an elevator, your weight will be different. The weight that the scale reads, the scale will read something different than your weight if you're accelerating upwards or downwards. Okay? And finally, the last case is when the object is on an incline. This might not be obvious, but we'll look at a couple examples. When an object is on an incline, the normal force is not equal to the weight of the object. A scale would not read the actual weight of the object. Okay, so we'll look at that in more detail in a second. But I want to do one other example looking at apparent weight. Okay, so press pause, read through this, press pause, try to work through this on your own. So my free body diagram is going to look like this. I have gravity pulling down on the groceries and pushing up on the groceries. I'm calling that force the force of my hand. You could also call this a normal force if you wanted to. And when the question asks, how heavy does the bag feel? That's like asking, what is the force that your hand is supplying to the groceries? So we're trying to figure out what is this force. Okay, so here's my free body diagram. I'm going to look at my net force in the y direction, so it'll be the force of the hand minus the force of gravity. The force of gravity is always equal to mg. Here I've plugged in the values, so the net force in the y direction is equal to the force of my hand minus 98. I can also say that the net force in the y direction is equal to my mass times my acceleration in the y direction. My mass is 10 kilograms and my acceleration is minus 2. Why is it minus 2? Because we're accelerating downwards. So that has to be a negative 2 there. That means that no matter what, the net force in my y direction has to be negative 20 newtons. Well, this expression is equal to the net force in the y direction, so I can set those two things equal. And I can solve that the force that my hand is supplying to the groceries is 78 newtons. If we were not accelerating, my hand would have to supply 98 newtons to support those groceries. But because we're accelerating downwards, I don't have to push up with as much force to support those groceries. I only have to push up with 78 newtons. Okay, so this is a case where the normal force or the apparent weight is different than the actual weight, and that's because we're accelerating in that vertical direction.